vamos a empezar. Veo que somos 47 conectados, que no es mal número. So, thank you everyone for attending this this presentation. I hope most of you already know me. I'm Luis Fonseca. I'm currently the leader of the MESSI group, and in a few days or weeks, the director to be of CNM. Once I become director, I will quit the role of group leader. So my role here today is to explain you this project, the project Epistore, that is has started the 1st of January. So it's a very recent project. Okay, I will try to show you which are the generic lines of the project, but also concentrate on the role of CNM in this project. So the name is Epistore. You see here the subtitle is Energy in Thin Layers, but of course, as any other project, has a very long name. In this case, it's Thin Film Reversible Solid Oxide Cells for Ultra-Compact Electrical Energy Storage. It's one of those titles where every word is a keyword. And I hope that by the end of the presentation, you are able to identify all these keywords and why they are key. Okay, so this is a project within the FET, the Future Emerging Technologies program. It was granted in the last call of H2020. You know that FETs are coming in both in two types. Ones that are produced bottom up, so the researcher puts forward a research topic, but there is another brand that is the proactive, where the commission sets the topic and then people apply to them. In this case, it was a FET proactive, and the topic of the call you can see here. It was breakthrough zero emissions energy storage and conversion technologies for carbon neutrality. So this is an energy project, okay? You maybe also know that the FET program disappears in Horizon Europe, so the next framework program, because the idea was so good that the Commission wanted to extend it farther beyond that ICT, that is where it was originated. And now in Horizon Europe, they have invented this EIC, that is the European Innovation Council, something that tries to replicate the European Research Council. And they have moved here all the breakthrough technologies projects that, and they will try to accelerate them also towards market applications. And these 5 projects will become what is written here, the Pathfinder scheme within this IAC. In fact, this last call was thought to be in between these two framework programs, and in a way it's participating in a kind of pilot Pathfinder EAC program. Okay, the project will last for 4 years. It involves a budget of 4.5 million euros, of which roughly 500,000 will reach CNM. It involves 12 partners from 6 countries, okay? And you can see here, which is the distribution of the different companies and research institutes that are involved in the project. We have some UK partners, so we will see what the Brexit means for an European project. Okay, the project is built around a main device that is a solid oxide cell. So this is just the reunion of 3 materials acting as an anode, cathode, and an electrolyte in between. And this device is able either of electrolyze water and produce hydrogen, or use hydrogen as a fuel and produce power. So in this row, in the upper row, here we are looking at a power to gas scheme. Okay, so we are converting power into a gas fuel that usually it's hydrogen. Okay, when this power comes from a renewable source, then we are talking that we are producing green hydrogen. Okay, and these cells, these electrochemical cells, are called solid oxide because differently from other sort of arrangements where the electrolyte is liquid, here the electrolyte as well as the anode and the cathode is solid, and usually it's an oxide material. Okay. Since in this structure something should move along, usually here in this case is oxygen ions. Of course, moving atoms in a solid is a hard thing to do, and for that these devices operate at high temperature. So solid oxide cells are high temperature devices, and this is something important to consider. Okay, and it's reversible because the same sort of device can do both things. So can turn power into hydrogen and can turn hydrogen into power. Okay, and thin film because the target of the project is try to build a very compact, this ultra compact keyword that appeared in the title, and for doing that we need thin films, advanced thin films, these complex oxides. And here in the last line, also the use of thin films is important in order to reduce the content of what is known as critical raw materials. Okay, so if anyone is looking for a question for at the end of the presentations, I could very well welcome someone asking what are a critical raw material, and I will be very happy to explain you. And the other important thing here is that we are talking about renewables for this approach because you know that renewables are getting more and more introduced, but one of the problems is that they produce energies that is not well aligned with the peak of demand. And sometimes we are producing energy with wind or solar that cannot be readily used. And store this energy, this surplus energy, is a problem, it's a complex problem. And this power to gas is a solution for that. Okay, so this, say this is the graphical abstract of the project. So we will start with some advanced materials, and they will be arranged in this anode, electrolyte, and cathode architecture, and they will put on top of a silicon platform. And here comes something interesting. This is something called silicon on nothing. So it's like silicon on insulator, but instead of having a varied oxide, what we need to produce here is a void, okay? Air, an air gap. This is why this is called silicon on nothing. And this is done in this way because then it's easy to transfer this thin skin of the silicon plus these active materials into another substrates, low cost substrates like metal that can be micro machined with gas channels to provide the fuels or to store the hydrogen or to put the steam, the water that needs to be converted into hydrogen. And in the end, what we want to do is something like a cube, because those layers can be stacked one top of another in order to add up all the energy or all the hydrogen conversion they can provide. And here you can see that we are talking about a cube of 3 by 3 by 3 centimeters, and this could provide even something huge like 1 kilowatt of energy in fuel cell mode. Okay. So those are the building blocks of the project. Of course, we have the electrical energy storage as a main application, and then we have all those advanced materials that I talked to you, that will be supported by theoretical simulations and characterization of those materials. And then those materials will be integrated all together into the silicon platform, the silicon on nothing. Okay. Here is how the expertise or the background of the different partners arranged in this vertical and horizontal strata. So in the vertical, you can see that partners divide between those having expertise in oxides and those having expertise on energy developments. And from a technological point of view, here in these horizontal layers, you can see that people are ranged from theoretical simulations to advanced nanotools, either for characterization or thin film deposition, till micro nanotechnologies for the integration of everything into a micro device that then will provide a compact cube of power. Okay. Again, this is another way of reordering the same sort of information, but here you can see which is the set of our packages of the project. And the main point here is just to show you that CNM, the main role of CNM is leading this work package 5, that is the one dealing with the integration of the materials into the silicon platform. So this is what we are not going to do. This is the material side, but of course, it's just for giving you a flavor of the sort of materials that the project is dealing with. So they are complex oxides with lots of funny elements. This is something related to the critical raw materials that I said in the beginning. And as you can see, they are totally alien to the silicon technology world. So this is one of the beauties and one of the challenges of the project. What we need to do is what is summarized in this slide, this silicon or nothing that I was anticipating. So we will start not with a silicon germanium substrate that it says here, but with a silicon substrate. And in order to be able to produce this silicon or nothing, to be able to produce this air gap below the silicon surface, we need to pattern the silicon with holes with a certain diameter, pitch, and to a certain depth, and then dispose the sample to a high temperature annealing, and then silicon evolves just by surface tension. The void that is rectangular or cylindrical starts to close, reaching a sphere, okay? And then you already are defining some silicon on top and some silicon at the bottom. And if the pitch is the adequate one, those spheres will coalesce all together, and then they will produce this continuous gap, okay? And as I said, the interesting point of this is that you can process this upper part, and then you can detach it and transfer to another substrate. And in the end, that's what we want to do. And integrate those materials into those sort of skins of silicon, and then be able to transfer them into another substrate. So just closing, I think this is just one of the last slides. Why are dealing this from a micro and nano perspective? As I said, the solid oxide cells, the O should be also in capital letters, are high temperature devices, and going micro is advantageous, and going micro and thin film is not only advantageous for the critical raw material issue, but also for other issues that deals with scale factors. So it's advantageous from a thermal mass point of view, because we will need less energy to heat up everything, and also the device will be able to follow fast transit responses, and this is very important for the application that we have in mind, especially if we are thinking of portable applications, and also because thin films exhibit, especially for ceramic materials, exhibit a higher strength under pressure, and these devices will be over pressure. Okay. And from a technology point of view, the things that we need to deal with at the clean room level for developing these sort of devices are high temperature boron doping. Usually we do this with solid sources because we need to define some Pli++ KOH resistant regions. We need, as I explained to you, some submicron featuring, but not really stream. Those diameter and pitch of the holes that we need to produce in the silicon can be around half a micron. So this can be attempted by e-beam, nanoimprint, DUV, if we end up having one, but even with the stepper, it's at the limit of the stepper. And also, we need to be able to perform thermal processes at high temperature, and this is important, and hydrogen atmospheres or very, very, very clean argon. Okay, if not, you cannot get those pillars becoming spheres and then it's becoming a surface silicon skin. By the way, this silicon skin will be 1 micron thick, and the air gap will be also 1 micron thick. Since we are dealing with external partners that need to put some strange materials onto our devices, probably when they these samples come back to CNM, we will need to process them at chip level, at 3x3 chips, for instance, and we will need to go through the MNC route in the clean room. For the previous steps, since we are on our own here, it could be clean, it could be MNC if whichever of the machines we need are clean or MNC, but this part is flexible. There is nothing imposing cleanliness or not cleanliness in the first part of the processes. Okay, and in the end, of course, we need to deal also with those transfer processes, and here maybe we can leverage some knowledge of the people working with graphene. So this is the last one. The people behind, the CNM people behind this project are Marc Salleras, Joaquín Santander, and myself. And since, as I said, I'm supposed to become director and my involvement will decrease, probably not my responsibility, but my technical involvement will be decreased, we have been able, with the money of the project, to recover some useful people like Íñigo Martín and Marta Fernández. So I think this is all for my part, and I will be happy to answer any questions that you may have. I hope all of you are still there. Okay, Frances has one question. You're welcome to do it.
Okay, Luis, thanks for the presentation. Okay, my question is about if you have evaluated if there will be some stress on the layers and if this could play a role. I mean, in this that is in layers.
In principle, the silicon itself should not be under stress, because it will be crystallographical silicon in the end. But it's true that once you start to put on top those other materials, then stress can build up. Indeed, we know from previous experiences that we have done those stacks of materials on top of silicon nitride membranes, and the overall stress is compressive, so they tend to corrugate or to buckle. But in order to try to avoid this, this area will be crisscrossed with those regions that I mentioned that were highly doped, and those will act as a kind of tensors in order to keep the membranes relatively flat. So we have a strategy for that, but you're right, and stress could play an important role here.
Okay, thank you.
Yeah, Ellie, the Epistore acronym is just something beautiful, but it's very challenging to try to find where every letter comes from. In fact, there is one P in this very long title, but this is a meaningless P. But anyway, if you look for it, you will find a P in the long title. Oh, David, thank you very much for this interesting question. What are critical raw materials? Okay. In fact, it's a very interesting concept, and it's not an absolute concept. One may think, okay, critical raw material is something that is scarce, that there is very little in the earth, and this is one component of that. But there are critical raw materials that are really abundant. Here, there are different problems coming together. In fact, there is an official list of critical raw materials at the European level. You can find this in the web. I think there is a list that is updated every 3 years. And the last one is from last year, 2020, and it contains up to 30 critical raw materials. And some of them are scarce materials, but many of them are materials that are concentrated in certain countries. Although abundant, they are concentrated. And maybe are countries that we are not friends with them, and they may suppose a criticality in trade. These countries maybe are concentrating the extraction or maybe the processing of those materials. So it's a geopolitical concept as well. And for sure, the list of critical raw materials of Europe is not the same that China. Okay, it's different because many of the European critical raw materials are critical because they are coming from China. For instance, lithium. Okay, and don't think that by critical raw material we are looking at the elements of the periodic table. Yeah, some of those materials are elementary, but others are other sort. For instance, carbon is very abundant, but natural graphite is a critical raw material in the European list. And silicon metal is a critical raw material. A lot of silicon is used when making steel, for instance. So it's a funny and interesting concept. The materials, these complex oxides, are well known. There are new avenues for producing novel ones, but the ones that will be used in the project mostly are well-known materials, but will be structured in a different way, in a way that makes them more performant. So from a chemical formulation are known, but from a technological perspective will pose a challenge. How scalable is this technology? If you mean the silicon or nothing, in principle, is scalable at wafer level. And ideally, this is not something invented by us. This is something that was proposed decades ago, just to try to, as an alternative to silicon on insulator. And also thinking on this possible transfer to another substrate, lower cost substrates. And one of the interesting things of this approach was that once you detach the silicon skin, you still have the wafer to repeat the process. So you are not wasting silicon. You can repeat this several times. So this is also adding to the scalability and the sustainability of the project. We are not really focusing on to those issues because the challenge is already quite important for just trying to get this at just a cheap level. Yes, it's true. This is something that was proposed for solar cells technology originally. The reduction of critical raw materials. The reduction, since I said it's not really coming from the formulation, the chemical formulation of the materials, is coming more for trying to do a device with thin films. So it's just reducing the material budget as a whole. This will reduce the critical raw materials involved in those materials. And in one of the slides, where the graphical abstract of the project, there was a little table below, and the goal is that just by going ultra compact, you could produce this 1 kilowatt energy with about 400 times less critical raw materials that a macro device, let's say, providing such power. So it's a huge decrease in these critical raw materials. Mm-hmm. So I guess the presentation will be available as I think any of the ones delivered in these talks will be. But nevertheless, if you have any question, you can always ask me anytime, anywhere. Miguel says, considering that it has to be maintained at so high temperature, is going to be efficient. Well, the cells can work in two ways. It can transfer power to gas, okay? And here, consider that we are trying to convert, to take advantage of surplus energy to convert it in hydrogen that will be available later on for other purposes. Some of them also for energy, okay? But in this aspect, we have lots of energy, so it's not a problem to maintain these things at high temperature. And indeed, you need high temperature to make the electrolysis of water. Okay. And in the other way around, if you want to use hydrogen as a fuel and produce power, the transformation of hydrogen into water or carbon dioxide produce power. It's an exothermic reaction. The only thing you need to provide is just the energy that you need to put the cell at 500 degrees. Once you have achieved this, then the reaction is self-sustained and has a net gain of energy. So it has an intrinsic efficiency. Yeah, I wouldn't advise handle something at 500 degrees with your fingers. This was just to, it was to show the size, not the way of handling it, okay? But it's true that these concepts are being developed for portable applications. So in the end, it should end up in something that you may carry with you. And then, of course, on top of this 3 by 3 by 3 centimeters, you will need to have insulation. And there are already some simulations of how thick should be the simulation in order to have an external temperature of something that is not harmful. Okay, so but probably you will need to add a couple of centimeters extra of width just for insulation. Packaging. The packaging that is considered an issue and a challenge in the project is just stacking 30 of those structured metal plus silicone skin stacks. Okay. But the extra insulation thing is not considered. Yeah, the silicon on nothing is a process that is patented and in fact is exploited and probably there is someone offering, perhaps is offered at some level. But it's like with any other technology that is offered. When you want to use it for your own purpose, sometimes the best way or the only way is that you do it yourself. And perhaps if we end up mastering these things, since we are kind of research institute with a flexible clean room, then we could end up offering flexibly this silicon or nothing for other purposes. More flexibly perhaps that any providers that could be around. Yeah, the silicon on top is crystalline. Is as crystalline as the original silicon with the same orientation. Defects can appear, especially if you are not careful with the cleanliness during the anneal that is favoring this silicon rearrangement. And if you have some problem or is inconsistency in the patterning of these original holes, then this will show up as a morphological defect, maybe a void in the skin or a pillar in the air gap where you didn't want it. Okay, but nevertheless, for instance, you could artificially introduce some errors in the patterning. For instance, if you want to leave some pillars, and this helps you to avoid, for instance, a sticking of the silicon skin onto the lower surface. This is something that is considered. But of course, you need also to consider that if you populate the silicon skin with too many supporting pillars, then this may jeopardize then the transfer, the peeling and transfer to another substrate. So there is a trade-off here between stability and transferability. Well, let's hope to have it in 4 years' time. Okay. So if there is no additional question, I think that we are at the end of it. If any question comes to your mind anytime, just don't hesitate to ask me anytime. Okay. Thanks to everyone for being there. I see that we were almost 60. That's great. I feel satisfied with that. Thanks to all of you.